Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about this problem. So let's get started. Let's see this problem. We are given a number and we have to swap all even and odd bits in binary representation of a given number. It means we have to swap all the even bits to its adjacent bit to right side, and we have to swap all the odd bits to its adjacent bit to left side. So to understand this problem better, let's see a few examples. So let's say if we have 5 as input, the binary representation of 5 is 0, 1, 0, 1. Okay? And if we swap all even bits to its adjacent right bits, and if we swap all the odd bits to its adjacent left bits, then our number becomes 1, 0, 1, 0. And the decimal representation of this number is 10. Let's see next example. In case of 10, the binary representation of number 10 is 1010, and if we swap all even bits with odd bits, it becomes 0101, and the decimal representation of this number is 5. So I hope now you understand this problem really well. So please pause this video and think about an algorithm to solve this problem. Okay, let's first see brute force approach to solve this problem. So the idea is really simple. Let's say we have a number 10 and the binary representation of this number is 1010. Okay? Here we are considering 32 bits numbers because in Java integers are represented in 32 bits. So we are going to create an array of size 32, and we are going to traverse this binary representation from least significant bit to most significant bit. And in each iteration we check if the bit is set or not. If bit is set, we store 1 in an array, and if bit is 0, we store 0 in an array. After this step, we traverse our newly constructed array and we swap all the even and odd position. Okay? After swapping, we again read all the values one by one from array and reproduce decimal number using those bits. Right? As we have stored 1 and 0s only, so we can reproduce decimal number using those numbers. Okay? So let's see how it works. So if n equal to 10 means 1010, we are going to store all the bits in an array. So after storing all the bits, the array looks like this, 0101, and then we swap all the even and odd position. So now it becomes 1010. Now we traverse all the elements in this array and multiply it with the power of 2. As we know that all the bits in binary representation represents power of 2. It means this bit represents power of 2 to the power 0, this bit represents 2 to the power 1, this bit represents power 2 to the power 2, and so on and so forth. So we are going to read all the values from left to right and we multiply it with power of 2. So 1 into 2 to the power 0 is equal to 1, 0 into 2 to the power 1 is equal to 0, 1 into 2 to the power 2 is equal to 4, and 0 into 2 to the power 3 is equal to 3. And we sum all the numbers. So after we do sum, we get 5. And this is the final result of this input. And if you see the binary representation of number 5, you see that all the even and odd bits are swapped. See here, the n is equal to 1010 and you get 0101. It means all the even and odd bits are swapped. So now let's see the implementation of this brute force approach. So this is the implementation of brute force approach. So what we are doing in this function, we are simply initializing an array of size 32 because we are considering 32 bits numbers. And in first loop, we are traversing from 0th bit to 31 bit and we are checking if bit is set or not. If bit is set, then we are pushing 1 to our array, and if the bit is not set, then we are pushing 0 to this array. Okay? Here I am using 1 left shift I. It means 1 is equal to 2 to the power 0. In each iteration, I am shifting the position of bit by ith position. Right? So for example, in first iteration the position of bit is at first position, and in second iteration the position of bit is at the first position, and in each iteration we are doing AND operation with n so that we can get that whether the bit is set or not at a specific position. Okay? In second for loop, we are again traversing our newly created array from 0 to 31 and we swap all the positions, and this time we are incrementing by 2. Because we are swapping position 0 and 1, and then we directly jumping to position 2, and then we swap position 2 and 3. so on and so forth. After second for loop, we initialized a variable answer equal to 0 and bit is equal to 1. Here the bit variable is used to calculate the power of 2. Okay, and then we are running a loop from again 0 to 31, and this is the expression where we are calculating the value of each bit. So initially the value of bit is 1, then it becomes 1 into 2 2, then it becomes 2 into 2 4, then it becomes 4 into 2 8. So this way we are calculating the power of 2 and we are multiplying this power of 2 with each bits we are getting from the newly created array, and we are adding it to our answer variable. Okay, and at the last we are returning answer. So let's quickly dry run this code and see how it works. So in case of 10, the binary representation of 10 is 1010. This is a 4-bit representation. Do not get confused. If you prepend all the zeros before this binary, it's not going to create any problem. Okay. So we are going to traverse this binary from LSB to MSB, and after traversing we push all the bits in an array, so it looks like this. And in second loop we just swap all the even and odd position, so now our array would look like this. And then we again traverse our array from first element to last element, and while traversing we are going to calculate value of each bit, right? So these bit corresponds to power of 2 to the power 0, these bit correspond to 2 to the power 1, these bit corresponding to 2 to the power 2, and so on and so forth. So we are doing just like this only. 0 plus 1 into 1, because the bit is 1, so it is equal to 1. Now this 1 plus the value of power, so the power of 2 is now 2 into this bit, so we get 1, and like this we are following. So when we complete this process, we get our answer as 5. Now talking about the time complexity of function, how many times loop is running and how many iterations are there. So we can say that our first loop is running 32 times, second loop is running 16 times because we are doing j plus 2 here. So every time we are incremented by 2, right? That's why the second loop runs 16 times and third loop also runs 32 times. So total time is equal to 32 plus 16 plus 32. Okay. So we can say that the overall time complexity of this function is theta of 1 constant time, or we could say that theta of number of bits present in the number. So this is the time complexity of this algorithm. But this code looks too lengthy. So can we do better? Do we have shorter implementation? Or can we solve this problem in less time? The answer to all this question is yes. Yes, we definitely write shorter implementation of this solution, and we are also going to solve it in less time. So let's discuss efficient approach to solve this problem. So let's see the idea of efficient approach. So we have n is equal to 10 and the binary representation of number 10 is 1010. So what is the idea? As we have to swap all the even and odd positions or even and odd bits, so what we have to do? So what we do here, in first step we are going to keep only even bits and we unset all the odd bits. So by performing this operation we are going to get one number. In second step what we do, we only keep odd bits and else other bits we are going to unset. So after performing this operation we are again going to get one number. And next step is we are going to shift our even number by one position, right shift. Okay, so the number becomes 0101. In next step we are going to shift our odd number by one position, left, towards left. Okay, so then the number becomes 0000. So after shifting even number one position right and odd number one position left, we are simply doing OR operation. So when we do OR operation, we get 0101 because 01 is equal to 1, 00 is equal to 1, 1 0 of OR is 1 and 0 of 0 of 0, 0 of 0 is 0. So we get our result and that is equal to 5. And this binary representation represents 5 in decimal, and this is the correct answer. So if n is 10, after swiping even and odd bits, we get 5 as our answer. Now the question is how to keep all the even bits and unset all the odd bits? Let's see how we do it. So we need a number whose all even bits are set, and that number look like this 101010, and we have this number, and the hexadecimal representation of this number is 0x 8 times a. Okay, so in this number all the even bits are set and all other bits are unset. So when we perform AND operation of a with n, we have all even bits remain and all the odd bits gets unset. So this is how we get our one number. In second step, we are going to keep all the odd bits and unset all the even bits. So for this also we have one number, and the hexadecimal representation of that number is 0x 8 times 5. So this number has all the odd bits set and all the even bits unset. So when we do binary AND with this number, we get a number where all the odd bits remain as it is and all the even bits gets unset. So we are done. We just have to shift the even number by one place towards right and odd number by one place left and do the OR operation, and we will get our answer. So let's see the implementation of this efficient approach. So this is a simple 5-line of implementation to solve this problem, and this 5-line corresponds to our 5 step discussed here. In first step, we are performing AND operation with number where all even bits are set and all odd bits are unset. So we get all the even bits. In next step, we are performing AND operation with a number whose all odd bits are set and all even bits are unset. So we get all our odd bits. And then we are right shifting all the even bits by one position and left shift all the bits of odd bits by one position. And at the last, we are simply doing OR operation between even bits and odd bits. So if n is equal to 10, we get output as 5. If n is equal to 5, we get output as 10. Okay, cool. So I think this is really a short implementation so far. So talking about time complexity, we are simply performing 5 constant operations. So the time complexity of this algorithm comes out to be theta of 1, that is constant. Okay. So now let's have a quick recap of what we have learned so far. So we are given a number and our task is to swap even bits with odd bits and odd bits with even bits. So we saw brute force approach to solve this problem. And the time complexity of brute force came out to be theta of 1 or theta of number of bits present in the number. Then we saw efficient approach to solve this problem, and that was also a shorter implementation. And the time complexity of efficient approach came out to be theta of 1, and that is a constant time complexity. So in brute force approach, our time complexity depends upon the number of bits present in the number, but in efficient approach, we are not dependent on the number of bits. We can simply swap all the bits of number in constant amount of time. So this is it for this video. Thanks for watching. See you in the next video.